Hello, my name is Ernesto Lee from Nesto.tv and Ernesto.net. And in this very important episode, I'm going to show you the math behind machine learning and deep learning. I typically like to stay away from the math because I feel sometimes that is intimidating to students and it turns a lot of people off. But I have been asked repeatedly to provide an episode that goes into the math behind deep learning. So if you have a mathematical aptitude, or if you're just interested in the machinery that makes this work, then I think this episode will be for you. I need for you to have a basic high school math background at least, though. We need to baseline it with that. Machine learning and deep learning, it requires you to understand algebra, probably linear algebra, and at least the basic calculus concepts. You don't need 3 years of college calculus to understand this. I'm going to explain a couple of calculus concepts that we need, hopefully in an intuitive and easy way. So let's start with, believe it or not, Scrum.org and Scrum Alliance and a lot of the agile-based organizations, right? Think agile. So I just happen to be Scrum.org certified. I'm a Scrum Master, and I do training in Agile. Now, if you're not familiar with Agile, the basic idea, it is exceedingly simple. We want to build something quickly. We want to get it deployed. We want to get some feedback on that deployment. And then we want to make changes based on that feedback. And effectively, at that point, you repeat the process, with the goal in Agile being to get your project closer to your customer so that you can incorporate your customer's feedback and use that as your compass, let's say. You want your customer's feedback so that you can create the best possible product with the least amount of error. Obviously, if you build the entire project and simply thrust that upon your customer, then you'll lose that valuable opportunity for your customer to contribute to the product, and therefore your risk of having a large error between what the customer expected and what you delivered is large. Disappointment. It happens when expectations do not meet reality. The steps needed for improving your product, they need to be small, and they should always involve your end user. So I was thinking, Agile software development, it's all about rapid iterations. The idea of, let's start with the solution as quickly as possible. Let's measure and iterate frequently as possible. You know what? That's actually gradient descent. It's basically gradient descent under the hood, and that is the main idea behind learning in most machine learning and deep learning models. Okay, so how do we get from the concept of Agile to the core formulas in machine learning and deep learning? And that's what I want to explain. I'm looking to give you at least the intuition with respect to the machine and deep learning process. Again, this is actually very simple and just includes some very basic high school math and a couple of concepts in calculus, right? Namely, the derivative. Through this episode, I want you to understand and I want you to be able to recreate effectively this formula in the context of a linear regression model. Keeping in mind, however, that what we're covering, it applies to other algorithms, but I wanted to start with linear regression because, frankly, that's one of the easier algorithms. So, a machine learning model, okay, let's consider, let's just say a bunch of data points that exist in a 2D space. Assume that the data is related to, let's say, the square footage and the price of a bunch of condos, or it could be related to weights as they relate to heights, right? It doesn't really matter. For the purposes of this episode, let's just imagine that we have some data points that roughly exhibit some linear types of attributes. We're trying to predict some kind of relationship between these quantities so that we can predict, let's say, the price of a new condo if we have the square footage, or we can predict the height if we have the weight, etc., etc. This is essentially a simple example of a supervised machine learning technique. So let's now draw an arbitrary line in space that passes some of these data points, right? Let's say it passes through some of these data points. And if we do that, then right off the bat, you can see that we have the equation of a line, right? That is y equals mx plus b, where m is the slope and b is its intercept on the y-axis. I am specifically calling out the change in y over the change in x because that's almost screaming at you that this is going to involve a rate of change. In other words, you can almost smell the derivative coming in calculus. So, in greater context, here is our algorithm in the context of the training process. It simply starts with a bag of data. In a parametric supervised learning scenario, we start with data that includes our features or includes our inputs, as well as the known result. When we have these inputs, we get this result, and we're going to use that to train our algorithm. This is the greatest use case, by the way, for machine learning, right? These supervised machine learning types of scenarios. There is an entire process involved in getting your data to this point, but for now, let's just assume that the data is ready. For simplicity, imagine that your data is in a tabular format and it looks like a spreadsheet or it looks like a table in the database. Take the first row and feed that to your algorithm. You have to know in advance what algorithm you're selecting, and you can choose from several. But in this case, remember, we decided that we were going to start with linear regression. And we said that linear regression algorithm was effectively, it was the slope of a line, right? Y equals mx plus b. But the fact that you, a human being, selected the algorithm means that this is a parametric use case, and you run the risk that the algorithm that you selected is wrong. Okay? At any rate, let's stay focused. At this point, you have an algorithm and you have a value for X or a value for your input that's supplied to your algorithm. So at this point, we're simply going to crunch the numbers and we're going to make a prediction. Notice that your input, it's only the X, right? Nothing else. M and B, they must be learned. Let me say that again. M and B, they must be learned. That is the entire point of machine learning in this context. For M and B, they really put a weight on the input values of X. The entire point in all of this is to find the best possible values for M and for B. We also call them coefficients. Now, look closely here. Your prediction is what we're going to call y prime. In the data set that you have the actual observed value of y. Y is your goal, right? We want to make a prediction that's actually close to y. We want our prediction, y prime, to be close to our goal of y, right? Y comes from your training set. Whenever you have the input values of x, we want our y prime to be close to our goal of y. In other words, you know the answer already. You're just supervising the algorithm to see how closely the algorithm came to getting the right answer. So at this point, one row of training data has been submitted to your algorithm and it has produced a prediction, y prime. We now want to compare what was predicted with what we already know, our y, in other words, our goal. And then we're going to grade this prediction in what we're going to call the loss function or cost function or error function. We simply take what was predicted and we subtract our goal, which again came from our original data set. And this is going to tell you how far off the prediction was from the real value. In other words, if let's say the square footage is 1,000 square feet and we predict the price to be 200,000 and the price is actually 175,000, then the cost function should show us $25,000. That's how far off our prediction was from the actual value. Finally, we have a graded result on our prediction. This is our cost, loss, or error function. That's really what that gives us. What we've done up to this point is we have calculated the error. We have calculated the mistake that our algorithm made. So here is the important part. What we have to do now is we have to learn from that mistake. Now, I cannot stress how important this optimization function is in machine learning. This optimization function is actually what separates machine learning from artificial intelligence. The difference between AI and machine learning is that in machine learning, there is a learning process. The optimization function is where the learning comes in machine learning and deep learning. Here, we need to take that error and the values for the coefficients of m and b, and we need to compute new and better values of m and b so that the next iteration of training we can have a better prediction. And how do we know that it's a better prediction? We know that because the cost function, which is a measure of the error or our mistakes, it's going to be lower the next time around. And we just want to get on that train and go round and round and round and continue to lower our cost function. We want to minimize our cost function. With those new values of m and b, it's going to start the entire process over again. Calculate the error, make the adjustment, run it again over and over. That's the name of the game, is to go in this circle until we have as low of a value as we can get for our cost function. Now, please let this sink in. I have seen too many blogs and experts, they really start with the X, Y, Z's and they skip over these A, B, C's. They start by diving into the math. They start by skipping over the context. I want you to understand the context at this point. What I just described, you need to be able to redraw this from memory and understand what each part is doing. So, I'm going to spend the rest of this episode describing each part and the math behind it. Let's start with the predictions. When you have a known set of inputs and their corresponding outputs, a machine learning model is going to try to make a prediction for a new set of inputs that will obviously occur in the future. But during the training phase, we'll have two values for the predictions. We'll have y, which is the goal, which comes from our training set, and we'll have y prime, right, which will be the prediction. Okay, again, y is the value that comes with your data set. Y is the value that we basically have from historical data. Y prime is the value that your algorithm predicted. After setting the coefficients, let's say to something random for the first pass only, we run it through the algorithm and we evaluate the output we evaluate the output, which is our prediction, right, which is y prime, and then we look at the known value, which is the goal that comes from the data set. Okay? Y is our goal. So, how good was the prediction? We need a way to measure the error. The error, again, it's the difference between what we predicted versus what we knew in the past that value should be given those same inputs. This is the idea of a cost function or a loss function or an error function. Technically, a loss function is for a single pass through, and a cost function is for the average of the error of many training cycles. We can go back to that later. For now, just know that the cost or loss function is a measure of the error in your predictions. What you see on your screen is a loss function, L-O-S-S, a loss function. And this is where the cost function fits in the overall training life cycle. As you can see, it takes the goal from the training data set and the prediction from the algorithm's output, and it gets the delta, right? It gets the distance between the two so we can see how far off our prediction is from our goal. Let's talk more about the cost function. The cost function, or the loss function, it evaluates the performance of our machine learning algorithm. The loss function, it computes the error for a single training example. That is the loss function. It's a single epoch. The cost function, on the other hand, is the average of the loss functions for all of the training examples. Just know that for purposes of this episode, I'm going to be using the terms cost function and loss function interchangeably, but technically there is a difference. On your screen, it's the true cost function. A cost function, it basically tells us how good our model is at making predictions for a given value of M and B. Let's say that there are a total of N as in Nancy, points in the data set, and for all of those N data points, we want to minimize the error. So the cost function would be the total squared error. Notice, we simply took the error, which is y prime minus y, and we squared that. We added that to the rest of the errors from the prior epochs or training cycles. And finally, we took the average of all of them over n number of epochs. In words, that is all that this equation is doing. That is the cost function. Here, I'm showing you the cost function for N as in Nancy data points as it fits in the training cycle for machine learning. Now, I really hope you are asking yourself why we take the squares of the differences and simply not, let's say, the absolute values of the differences. Okay? Why do we square that? Why is it not just y prime minus y, right? And the answer to that it's actually very simple. It's because these squared differences, it makes it easier to derive a regression line. And I chose that word derive very specifically. Remember, we are looking to find the best values for M and B in the equation y equals mx plus b, which is our algorithm, and this is our regression line. Here's the thing. To find that line, or at least the best values of M and B, we have to compute the first derivative of the cost function and it is much harder to compute the derivative of absolute values than it is squared values because of the power rule in calculus. Okay, I'll also cover that. Also, the squared differences, they increase the error distance. Okay, and that makes the bad predictions or the larger predictions, the larger errors in those predictions, it makes those more pronounced than good ones. In other words, we ignore smaller errors and we enhance or amplify larger errors when we square in the cost function. Okay? So for now, just know that we square the errors because it makes the math easier and it has no impact on our ability to make good models. I like going to this website I just showed you right here, https://www.desmos.com/calculator. And there's a graphing capability there. I like to graph the cost function with respect to a weight. It is essentially y hat, okay, which is a prediction, minus y, which is the known value of y, squared. You can substitute y hat minus y with simply error. And that means that it is really the error squared. Okay, and the error squared, that's your cost function or your loss function, that is the y-axis. The x-axis is going to be one of your weights. Minimizing the cost function. Okay, things just got real. The goal of any machine learning algorithm is to minimize the cost function. Let me reemphasize that. The goal of any machine learning or deep learning model is to minimize the cost function. What does that actually mean? Okay. I see all these blogs on the internet and they talk about running down a hill. They don't give you any context whatsoever. What does it actually mean to minimize the cost function? What that means in this case is that we need to find the best values of m and b for our linear regression use case that gives us the lowest error. And we said the error is our cost function. So how do we get the lowest cost function? We find the best possible values for m and b. Okay, that's because a lower error between the actual and the predicted values means that your algorithm has done a good job in learning. Since we want the lowest error value, we want those m and b values which give us the smallest possible error. But how do you actually minimize really any function? If you look carefully, our loss function, and similar to the cost function, it is basically cost function equals y prime minus y squared. The cost function, it's the y-axis. It is of the general form of y equals x squared. In a Cartesian coordinate system, this is the equation for a parabola. And it can always be graphed as a parabola, okay, represented as what you see on your screen. That was the reason why I went to that site and showed you how to graph the cost function. I wanted you to have context. That's where that parabola comes from. That parabola, we're graphing the cost function, the error, with respect to one of the coefficients, m or b. I've read too many blogs that talk about gradient descent as simply walking down the hill, but they never, ever show you where the hill is. This is where the hill comes from. If you simply graph your cost function on the y-axis and your input or your coefficient, which is m or b in our case, on the x-axis, in the form that I mentioned, y equals x squared, which is our cost function, you will always end up with a parabola. To minimize the function that you see on your screen, we need to find the value of x that produces the lowest value of y. Okay, let me say that I'm saying that from the point of view of the Cartesian coordinate system. But from a machine learning perspective, you need to find the best value of m that gives you the lowest cost value, right? The lowest error. Or the lowest, I should say, the lowest value of b that gives you the lowest error. Okay? And I have that represented as the red dot on your screen. In a two-dimensional case, it's very easy to locate the minimum, right? We made this a simple use case, so you can see that. It's very simple in a 2D graph. But I promise you, it will not be easy if you have three-dimensional space or if you have hyperspace, right? If you have multiple dimensions, it will not be easy to find that lowest point if you have multiple features. That's not always going to be the case. In cases of higher dimensionality, which frankly is going to be the reality for most real use cases, we need a mathematical way to compute the lowest value, right? And in those cases, we need to devise an algorithm to locate the minimum for that cost function, and that algorithm is called gradient descent. Gradient descent, it is one of the most popular algorithms to perform optimization, and it's by far the most common way to optimize neural networks. It is iterative, right? An iterative optimization algorithm. And we're going to use that to find the minimum value for a function. So hopefully that is sufficient context for you. Okay? So now you know how the parabola is created. Let's provide an intuition. Let's say that you're now walking along the graph that you see, and you're currently at the green dot there. And again, the idea is that we want to reach the minimum. The curve that you're walking on, it's the error that you've graphed, okay? And the dots will represent the value of m, okay? And we want to find a value of m that gets us to the bottom of the hill, okay? Where the red dot is. From your position, let's say, you're not able to see that minimum. So the possible actions for you in this space would be you can go up the hill or down the hill. And once you decide which way to go, you have to decide how big of a step you want to take. A big step or a little step. Here is the big point. Our goal is to reach the minimum, as I said, the lowest error in that graph. And to do that, there are two things that you must know: which way to go and how big a step to take. Okay? Those are the two things that you must know. The gradient descent algorithm helps you to make those decisions efficiently and effectively with the use of derivatives. That's right, I said it, derivatives. A derivative, it's a term that comes from calculus and is calculated as the slope of the graph at a particular point. The slope is going to be described by drawing a tangent line to the graph at that point. So if we're able to compute this tangent line, we might be able to compute the desired direction to reach the minimum. We're going to talk about this in more detail in the later part of the episode. The minimum value in the same figure that you see here, if we draw a tangent at the green point, we know that we're moving upwards. We're moving away from the minimum, and vice versa. The slope at the blue point is less steep than that at the green point, which means it will take much smaller steps to reach the minimum from the blue point than from the green point. the jumble of rules for taking derivatives, it never kind of clicked for me. The addition rule, the product rule, the quotient rule. I really don't like the way that math is taught in my country, right? How does it fit together? Where's the intuition? How does this really apply to anything? What are we even trying to do? So remember, I'm talking about derivatives, right, in calculus. And this is kind of my take on derivatives. We have a system to analyze. Our function f is the system that we're trying to analyze. The derivative of f, which is f prime, also df over dx, it's the moment-by-moment behavior, in this case, of the cost function with respect to one of the weights. As it turns out, f is part of a larger system. H equals, let's say, f plus g, right? With our function being f. So using the behavior of the parts, can we figure out the behavior of the whole? And the answer to that, of course, is yes. Otherwise, I wouldn't have asked the question. Every part has a point of view. Remember, calculus, it's all about looking at the system as a whole and then evaluating it from a singular point of view. Okay? And that single point of view is about how much it changed if another part of the system changed. Okay? How much change was added if another part of the system changed. Combine every point of view and you get the overall behavior. Each derivative rule in calculus, it's simply an example of merging various points of view. In machine learning, we need the point of view of the cost function and the point of view of the weight, m or b. In other words, if I change the cost function, how does that impact the weight? This deep insight is what allows machine learning to work. And why don't we analyze the entire system all at once, right? And that's the same reason you don't eat a hamburger all at once, right? Because the smaller parts are easier to wrap your head around. So instead of memorizing separate rules, I want you to see how they fit together. The goal is to really understand this kind of notion of combining or collapsing perspectives in a machine learning system. Let's just take a look at addition, multiplication, powers, and the chain rule and how they apply to machine learning. Okay? Functions. Okay? Whenever I think of a function, at least as it was taught to me, the very first thing that the math professor would do is they would throw up a graph. Okay? That's the default go-to, is to throw up a graph. Okay? And the default calculus explanation would write f of x equals x squared, and they would throw the graph in your face. Okay? That really does not help you with your intuition. Okay? Not for me, at least. What the graph is doing is it's squashing the inputs and the outputs into a single curve, and it's hiding the machinery that turns the input into the output. But the derivatives, those rules are about the machinery. Okay? So it's counterproductive to start off teaching calculus by shoving graphs in your face. When I think of a function, I visualize that function as the process. The input, which is x, will go over to my function f, and it's going to give me an output y. Think of the function f as a machine, and that machine has a knob or a lever that I'm going to call x, and it has an output lever that I'm going to call y. Okay? here is the key insight for calculus. As I adjust my value for x, my function is going to set the height for y. Think of this analogy. X is my input signal. F receives it, does some magic, and poof, it sends out the signal y. Use whatever analogy helps it click for you. Okay? I like to think of it in terms of wobbles. Okay, that's what the machine is. That's what the derivative is. The derivative, again, it's the moment-by-moment behavior of your function. What does that mean? Okay, and don't just mindlessly mumble, the derivative is the slope. When people tell me that, that tells me that they don't understand intuitively what a derivative is. Okay? The derivative is how much the inputs wobble with respect to the outputs or vice versa. The lever is at x. We wobble that lever. So in other words, we wobble the value of x, and we see how y changes. Okay? We move the input lever, let's say we move the input lever 1 inch, and the output moved 5 inches. The results can be written as the output wobble per input wobble, or d sub y over d sub x. Okay? Or let's say 5 inches divided by 1 inch equals 5, right? This is usually, a formula, not a static value, because it can depend on your current input settings. Okay, so let's go back to the example that's going to be most relevant to us. When f sub x is equal to x squared, we said y equals x squared, right? That's our cost function. X being the error squared, f of x being y. Okay, if you've taken any calculus class and passed, then you know that the derivative of x squared is 2x. And you probably know that more so because you memorized it, not because you intuitively know what that means. Okay? So think about the machine I was talking about. Let's say that our input lever is x equals 10, and we wobble it slightly, and we move it so that the change in x, which I'm going to call dx, equals 0.1. Okay, that's the change. So overall, x equals 10 plus 0.1, so now it's 10.1. Okay, x is now at 10.1. X plus the change in x, okay, 10 plus 0.1. The output should change by dy. Okay, how much exactly though? We know that the derivative of f of x, or f prime of x, equals dy over dx, and we know that that equals 2x, because x squared, the derivative of that, equals 2x. So at x equals 10, then the output wobble per input wobble is equal to 2 times 10, which equals 20. The output moves 20 units for every unit of input movement. If the change in x, or dx, equals 0.1, then the change in y, or dy, equals 20 times dx. And I said dx equals 0.1, and that equals 2. And as you can see, the difference between 10 squared and 10.1 squared is about 2. The derivative, it estimated how far that output knob would move. Right? A perfect, infinitely small wobble would move 2 units. Right? We move 2.01. So the key to understanding the derivative rules are this. Set up your system, right? That's why I wanted to go through all of this so that I can stage my cost function, because I'm going to be taking the derivative of my cost function. Wobble each part of that system. I'm going to take my cost function and I'm going to wobble the value of M and see what that does to the system. Wobble the value of B and see what that does to the system. So wobble each part of the system separately. See how far the outputs move. And then we're going to combine the results. The total wobble is going to be the sum of the wobbles from each part.